Hi to all. I am Vempati Srinivasulu, Assistant Professor of Chemistry, working at Nagarjuna Government Degree College, Nalgonda. In the previous classes, we have discussed different parts belongs to Carbanians 1, which is in the syllabus of BSc second year, third semester chemistry. In this Carbanian 1, we have discussed what are carbanions, how they are generates, how they generates, types of carbanions, stability of carbanions, what factors stabilizes the stability of affects the stability of carbanion, then followed by acidity of alpha hydrides in different compounds. Then we have been discussing some organic synthetic reactions or organic named reactions involving in carbanion. Before that, we have discussed what is a tautomerism, what is tautomerization, how a one tautomer converts into another tautomer, what are the factors favoring the concerned tautomer in more percentage, and also we have discussed tautomerism in different classes of compounds. Those include carbonyl compounds, nitrohydrocarbons, and different uh, compounds. After that, we have discussed carbanion involving reactions, especially aldol condensation, then benzoin condensation, then Perkin reaction. So these three reactions we have discussed with examples and mechanism. Today we are going to remaining part of this carbanions 1 chapter. We are going to finish this chapter today. What we are going to discuss is haloform reaction, terminal carbanions, terminal alkynes. Then how can we prepare or synthesize higher alkynes from lower alkynes? So these three parts we are going to discuss today. First, we are going to start about we are starting topic is haloform reaction. Okay, what is haloform reaction? We see haloform reaction is generally we observe. Oh, actually, what is haloform? CHX3 we call as haloform. This is CHX3 in general. Trihalomethane 111 trihalomethanes are in general called as haloform. For example, in the place of X we have Cl3 we call as chloroform. This is called bromoform. This is called iodoform. Okay. So why these are calling haloforms? This CHX3 on hydrolysis in presence of base, it is giving formic acid. That's why these are called haloforms. So chloroform, bromoform, iodoform, and chloroform. So this is a haloform. So what is haloform reaction? So generally methyl ketones and potential methyl ketones. These two classes of compounds generally exhibit this type of reaction, haloform reaction. So what is happening in haloform reactions is, for example, you see this is one compound. is a methyl ketone or COCH3. So we see carefully we have a COCH3 group. This methyl ketone in presence of halogen and base both are in excess quantity, it is giving a carboxylate ion and with CHX3, that is a haloform. Okay, so this is an example general reaction for haloform reaction. So in the case of in the place of X2 we take chlorine, we'll get chloroform. Okay, in the place of X we take chlorine, chloroform. If you take bromine, we get bromoform. If you take iodine, we'll get iodoform. Okay, so one more example here it is in the place of R it may be H or CH3. If it is H, it is called H toluene. If it is methyl, it is maybe acetone, or it is maybe phenyl. In the place of R, it may be H or methyl or phenyl. If it is phenyl, we call as acetophenone. Okay, then coming to the second reaction. What is this? You see this one, acetaldehyde, ethanol, acetaldehyde, ethanol, not ethanol, ethanol. In with the halogen and base in excess quantity, it is giving acetation and haloform. So this is another example for haloform reaction. If you take acetone with iodine, excess of NaOH or KOH, we are getting potassium acetate and iodoform CHI3. You see, this is CHI3, iodoform. If you take bromine, you get bromoform. So in general, it is a haloform reaction. We'll discuss another example. It is acetophenone. So in methyl ketone, in the place of R, we have taken phenyl. That is acetophenone. Phenyl methyl ketone. This is called phenyl methyl ketone. Okay. This phenyl methyl ketone, in this excess of halogen and NaOH, it is giving benzoate, sodium benzoate and haloform. So these are the different examples for haloform reaction. So what is haloform reaction? The organic compounds containing methyl ketones or potential methyl ketones. So what is present we will discuss in the next slide. So the organic compounds containing methyl ketones or potential methyl ketones, when they react with halogen and base, both are in excess quantity, they are giving sodium or potassium, and that means a salt of carboxylate ion, and followed by formation of haloform. That's why we call these reactions are haloform reactions. Next. Okay. We see. Okay. This is a ethyl alcohol. Just now I told you potential methyl ketones. You see this CH2OH is there, which is attached to a CH3 group. It is called potential methyl ketones. Why? Because on oxidation, it is giving our methyl ketones. With halogen and base, these are alcohols that give methyl ketones. These are called potential methyl ketones. For example, ethanol, ethyl alcohol, or 2-propanol, all these comes under potential methyl ketones. So these potential methyl ketones also in presence of base and NaOH or KOH, they are giving haloform reaction. Okay. So one more example, acetophenone. You see acetophenone, and this is a okay. Next slide. It is acetophenone. In this iodoform reaction, it is giving CHI3. So this is called iodoform test. Generally, when we compare this chloroform, bromoform, and iodoform is somehow stable. Further, because of high molecular weight, it forms its solid state. That means it precipitate in as a yellow in color. So that's why this reaction is used to identify methyl ketones or potential methyl ketone containing organic compounds. So this is iodoform test. This is important one where it is asked in so many examinations. So what is iodoform test? It is used to identify methyl ketones or potential methyl ketones in the given organic compound. What is the reaction? When these organic compounds containing methyl ketones, they react with iodine with excess of NaOH or KOH, it is giving CHI3 in addition to carboxylate salt, acetate salt or any carboxylate salt. So this CHI3 forms in yellow crystalline as a crystalline compound in yellow color. That's why it is termed as iodoform reaction. Okay, what is the mechanism? So in the iodoform reaction, what is happening? We see carefully. Okay. Okay. So this is, we have taken an example. CH3COR. In presence of excess in NaOH and KOH, it is giving sodium salt of carboxylic acid and CHI3. So we are taking this reaction for mechanism. Okay. So what is happening here is, we see in the first step. So NaOH or KOH easily ionized to corresponding ions, it is giving OH minus. OH minus abstracts a proton. Why proton? So because of this carbonyl group, which is highly electronegative because of oxygen, this bond pollution takes place. Because of this electrophilic center, this alpha hydrogens becomes acidic. Already we have discussed in the earlier classes. That's why this hydroxide ion abstracts a proton from here, generates a new carbanion. This is a new carbanion. It is delocalized to this enolate ion. This is enolate ion. So first it forms a carbanion and it resonates to give more stable enolate ion. So this is enolate ion. So it is in conjugation with carbanion. So this carbanion in presence of halogen, it due to delocalization, this minus charge attacks halogen and one halogen is going as. There is a nucleophilic substitution reaction. So one nucleophile, this is a one nucleophile, this minus charge is attacking chlorine. So this real X is going as X minus. So what is happening here in this reaction, this step, it is a nucleophilic substitution reaction. Okay, so after this reaction, we are getting one halogenated, alpha halogenated, our organic compound, starting compound. This on further reaction. Why? Because you see carefully, there are two more hydrogens, 1 and 2. These two hydrogens also acidic in nature. That's why in consecutive reactions, what happens? This hydroxide abstracts a proton from here, forming same carbanion. This carbanion once again reacts with halogen by giving dihalo ketone. There is one more hydrogen. This is also more acidic. Why? Because it is more acidic. Why? Because you see two halogen groups and CO group. All these are highly electronegative. So that's why these are electron withdrawing. Due to electron withdrawing nature, this carbon attracts bond electron with H. That's why H becomes polar. 3H bond becomes polar. That's why in the presence of base, it easily goes as a proton. So whenever hydroxide ion abstracts a proton from here, it forms its corresponding carbon ion. This followed by in presence of halogen, it is giving trihalogenated. You see carefully, it is trihalogenated, our starting compound. XXX. Three halogens are replaced hydrogens. Hydrogens are replaced by halogens. So this is a trihalogenated our starting compound, methyl ketone. Okay. Then this trihalogenated compound, what happened here? Further hydroxide attacks. So since there are no alpha hydrogens, even though there are alpha hydrogens, those are not. Then this hydroxide ion attacks carbonyl carbon. Why? Because the carbonyl carbon acts as an electrophilic center. If there are no alpha hydrogens, it attacks carbonyl carbon, forming this type of O minus ion. This O minus ion, on electron delocalization, is giving an acid and a CHX3. You see CX3 minus carbon ion. You see it is a CX3 minus and acid. CX3 means H hex X X. You see CX3 is CX3 minus a strong base. Why? Because it is having more. Okay. It disturbed from some point of time. It is here. Okay. Right. Okay. Then it attacked OH on the CO group, results in acid and CX3 minus. Because of strong base, conjugate base, it abstracts proton from acid. Acid is a easily donates proton. By donating proton, it forms its corresponding stable carboxylate ion. It is stable than acid. That's why it gives a proton to this by forming this. So both are stable. CHX3 is stable, this is stable. So on acidification, we will get the acid and haloform. So this is the mechanism of haloform reaction. In haloform reaction, what happens? First, three hydrogens undergo substitution reaction with halogens through nucleophilic substitution reaction in presence of base. In these three reactions, we are observing formation of carbon ion. Due to a nucleophilic substitution reaction of carbon ion, it is halogenated. It is undergoing halogenation. So trihalogenated, our starting compound, further reacts with hydroxide ion. It is giving a O minus oxide ion. On delocalization of electrons and the bond breakage, we are getting acid and CX3 minus. Because of basic nature of CX3 minus, it abstracts from acid by giving halo form. So in this reaction, we are observing formation of halo form. That's why we call this reaction is haloform reaction. Generally, we observe iodoform reaction. Why? Because iodoform CHI3 is stable and precipitates as a solid, whereas chloroform and bromoform is in liquids. That's why we can't separate. They are not separated. out. That's why those are not useful. That's why we use iodoform test to identify COCH3 group or this type of potential methyl ketone group in the given organic compound. This is about haloform test or iodoform test. Next slide. So in our lecture we are going to discuss about one more term, terminal alkynes. You see, terminal alkynes. We know what are alkynes. Alkynes are hydrocarbons having C triple bond C triple bond C triple bond C. These carbon compounds contain this structure functional group we call as what? Alkynes. Okay. Alkynes are two types. Terminal alkynes, non-terminal alkynes. So what are terminal alkynes? Terminal alkynes, and that means a triple bond is there in the compound at one terminal. In other words, this bond should contain a C triple bond H, a hydrogen is linked to triple bonded carbon. If the alkyne, in alkyne, triple bonded carbon, or at least one of the triple bonded carbon is linked to hydrogen, we call those are terminal alkynes. You see, for example, this is one example. This is also only one terminal, ethyne. This is a propyne, and this is a 1-butyne. Why butyne? 4 carbons, numbering 1, 2, 3, 4. That's why 1-butyne. All these examples, these are examples for terminal alkynes. So what are non-terminal alkynes? You see, this is a non-terminal alkynes. Why? Because C triple bond C is not in one side, one terminal. In between, this double triple bond is in between. That's why this is a non-terminal alkyne, 1-butyne. This one also non-terminal. Why? Because you see 1, 2, 3rd carbon. Or from here also 1, 2, 3, 3rd carbon. It is a 3-hexane. 3-hexane is also example for non-terminal. Why? Because this triple bonded carbon doesn't have any hydrogen. That's why it is classified as non-terminal alkynes. So alkynes are the substances with carbon-carbon triple bond. These are two types. One is terminal alkynes, which are having hydrogen at one terminal. Hydrogen is attached to triple bonded carbon. In non-terminal alkynes, we don't observe hydrogen which is linked to triple bonded carbon. Okay, already we have discussed that hydrogen linked to triple bonded carbon, this shows some acidity, acidic in nature. So hydrogen linked to triple bonded carbon, it shows weakly acidic in nature. So we'll discuss what is why. So generally, see, hydrogen linked to sp3 carbon, or hydrogen linked to sp2 carbon, or hydrogen linked to sp carbon. So why hydrogen linked to sp carbon is showing acidity? This is explained in terms of S character. So in sp3 carbon, it shows 25% S character. In sp2 hybridization, S character is 33%. In sp hybridization, we observe 50%. So what happens in these carbons? S character is increasing from sp3 to sp. When carbon percentage increases, electronegativity also increases. Why? S atoll is at the center. That's why electrons attracted towards the center. It is from nearer to the nucleus. That's why electrons are attracted towards the nucleus. Thereby, bonded electron is attracted towards the carbon in the case of sp3. That's why that CH bond is polarized. Due to this polarity, hydrogen, if it is linked to hydrogen goes as H plus. Any substance it is giving proton, it is called as acid. That's why triple bonded hydrogen linked to triple bonded carbon shows some acidic nature. So this acidity is not strong as in our mineral acids or in acetic acid or carboxylic acids, but somehow acidic, weakly acidic. This SAP, we will know the pK values of this hydrogen linked to triple bond carbon is 25. So weakly acidic. In ethylenic hydrogen, it shows 44 pKa. In alkane, it shows some more. pKa value decreases, acidity increases, as we know that. So due to this reason, acetylenic carbon or hydrogen linked to terminal in terminal alkynes, it shows acidic nature. Due to this acidic nature, it forms its corresponding carbene ion. Why? Because carbon is negative charge. As we know, carbon with negative charge we call as carbene ion. So carbon ion generation takes place. So this acidity is confirmed in this reaction also. We see this reaction, propane in presence of NH2 minus amide ion like sodamide or lithium amide, it forms its corresponding carbene ion and ammonia. It is a acid base reaction. What is happening here? This propane is losing one proton to this amide ion. So it is an acid, it is a base. It is a conjugate base, it is a conjugate acid. We know that. Bronsted-Lowry theory. So that's why this propane is show some acidic nature in presence of bases like amide, not in the case of NaOH or KOH. So okay, especially it requires strong bases only, like NH2 minus. Okay, then we see in another reaction. Okay, when this propane is reacted with sodium metal, it forms corresponding carbon ion and a hydrogen gas. We know that acids when react with the reactive metals, when they liberates hydrogen. In this term also we can explain the acidic nature of this terminal alkynes. So these terminal alkynes in reaction with sodium metal, they are generating hydrogen gas by giving corresponding anions, carbene ions. These are called acetylides. All clinide, which is acetylene, we call acetylides. So this is something about the carbene ion in alkynes. How we identify these terminal alkynes? So terminal alkynes are alkynes in which triple bonded carbon is at one corner, one end. These contain a specific acidic hydrogen. The terminal alkynes has a hydrogen which is linked to triple bonded carbon. So how can we identify in the laboratory? So by using these two tests, one is with the Tollens test. Okay, this is the Tollens test, and it's the reaction with the ammonical Q plus chloride. With the Tollens reagent, what is Tollens reagent? Ammonical silver nitrate is called Tollens reagent. That means AgNO3 and aqueous ammonia. That means ammonium hydroxide. The mixture of these two we call as Tollens reagent. In presence of Tollens reagent, it forms its corresponding silver acetylides, silver alkylide. If you take acetylene, we'll get silver acetylide. This is a silver precipitate in white color. So formation of white color, a alkyne with silver ammonical silver nitrate, if it forms white precipitate, we can say that is a terminal alkyne. For example, if you take acetylene, you see acetylene, it is acetylene ethyne. We have two hydrogens, two acidic hydrogens. These two acidic hydrogens are replaced by two silver ions, Ag+. It is called silver acetylide, Ag2C2. This is in white color. Okay, so acetylene or any terminal alkyne forms white precipitate with what? With ammonical silver nitrate, which is what we call is Tollens reagent. That means in the Tollens test, if an alkyne gives a white precipitate of silver acetylide, we'll say that is a terminal alkyne. One more example, ammonical cuprous chloride. You see, ammonical cuprous chloride, Cu2Cl2. This Cu2Cl2 in the presence of ammonium hydroxide also gives some cuprous salt, reddish brown PPT. Same acetylene also gives this type of Cu. These two hydrogens are replaced by our copper. We call these are copper acetylide. Okay, that's why it is called copper acetylide. So one thing is clear. So we can identify our terminal alkynes with these two reagents. One is Tollens test. In this test, it forms white precipitate. Another is reaction with ammonical cuprous chloride. If these terminal alkynes gives a reddish brown PPT with this ammonical cuprous chloride. With these two reactions, we can identify or we can differentiate terminal alkynes from non-terminal alkynes. Coming to the next part of this session is a synthesis of higher alkynes from smaller alkynes. So alkynes are the substances with carbon-carbon triple bond. This from smaller alkynes we can synthesize higher alkynes. In this reaction we are forming a new carbon-carbon bond. We are adding an R group to the acetylene. Because of acidic nature of hydrogen, these hydrogens are easily replaced by other nucleophiles. By using this concept, we are synthesizing higher alkynes. You take one example here. So you see, this is a alkyne with the reaction with sodium. It forms its corresponding sodium alkynide. Another reaction. Okay, reaction of this generated carbanion when react with the alkyl halide. You see carefully, this is a carbanion. When reacts with the alkyl halide on nucleophilic substitution. Why? Because this X is going as X minus and this carbanions are replacing this X place in alkyl halide. We are getting this alkyl substituted alkyne. So this is our starting product reactant. You see, this is our starting reactant. This is our end product in this reaction. What is the change? We have replaced this hydrogen with R. So alkylated alkyne. So in this way, one alkyne is transformed into another alkyne. So this is a one type of upgradation. So we have one more one method converting these alkynes into Grignard reagents. You know what is Grignard reagent? Alkyl, methyl, alkyl magnesium halide is called a Grignard reagent. For example, RMGX. So whenever this Grignard reagent reacts with our terminal alkynes, it's formed corresponding Grignard reagent. So you see, this is a carbonate, this is a carbonate, and this is a one new Grignard reagent. So alkynyl magnesium halide is a new Grignard reagent. In the same place, this R is converting into a alkane, RH. We know that this is also a proof for acidic nature of our alkyne. So when acids, when they react with gradient, they generate alkanes or corresponding hydrocarbons, which is present in our Grignard reagent. So it forms its corresponding Grignard reagent. This Grignard reagent, when it reacts with an alkyl halide, it is substituting halogen in this compound. X is going as X minus. This is a net reaction. The final product is this one. What is happening here? You see, this is a starting compound. It is our product. So what is the difference? You see, in the place of one hydrogen, it is replacing one alkyl group. That means number of carbon in this is 3. We see in this carbon is 1, 2, 3. I mean one carbon is more or one alkyl group is more. Depending upon the nature of a carbon in alkyl group, we can synthesize any type of alkyne from lower alkynes. You see how. Okay, one example from ethine to propyne. You see, ethine to propyne. Ethine is an alkyne with 2 carbons. Propyne is also alkyne with 3 carbons. So what is the net change? 1 carbon. So though both are alkynes, one carbon is added. That means upgraded. You see what is happening here. So acetylene, ethine. When ethine reacts with sodium metal, it forms its corresponding acetylide, as we know. This acetylide is react with methyl chloride. So this chloride is replaced by this carbanion. We are getting this compound. What is happening here? This methyl group is attaching to this alkyne. So this is the net reaction is you see net reaction. So this is ethine, this is propyne. What is the change? One of the hydrogen is replaced by methyl group. So 2-membered alkyne is converted into 3-membered alkyne. That means higher alkyne. It's ethine. This one is propyne. So this is a one way to prepare one smaller alkynes to higher alkynes. We'll go one more example. What is this? Ethine to 2-butane. You see carefully, our target is to prepare what? Ethine, 2-membered carbon, ethine. We have to get 4-membered carbon, butane. 2-butane, not terminal, it's a non-terminal. So what is the change here? These two hydrogens are replacing by 2 methyl groups. I think you understood what we have to do. So these 2 hydrogens, if you convert into corresponding carbanion or ylides, carbanion, these carbanions are easily react with alkyl halide to form corresponding alkylated alkynes. We see what to do step by step. In the first step, this acetylene reacts with sodium metal. It forms its corresponding sodium acetylide. This sodium acetylide on reaction with the methyl bromide, this minus charge carbanion replaces this halogen this X goes as Br goes as Br minus. This minus charge is replacing this halogen. That's why we are getting one alkylated alkyne, that is propyne. So this is not our required product. We have to prepare 2-butane. That means here is we have observing one more hydrogen. It is to be replaced by one more methyl group. So for that, if you convert, if you can perform one more step, that is first sodium with sodium metal, then followed by methyl chloride or methyl bromide, we are getting 2-butane. So from this acetylene or ethyne, we are preparing 2-butane. So that's why it is an upgradation reaction. We are preparing higher homologue from the lower homologue with the same functional group. This is one example for upgradation of alkynes into higher alkynes. So this is one example, ethyne to propyne. And one more example, ethyne to 2-butane. One more example. See, propyne, we have to prepare propyne to 2-hexane. So what is happening here? Both are alkynes. Okay. Then we have to synthesize 3-membered alkyne to 6-membered alkane. So what we have to do? We have to add 3 carbons to this propyne. So for that, what we have to do? First, this compound has to convert into this carbon. This compound has to convert into corresponding carbanion by losing sp proton. Then we have to add a 3-membered carbon, straight chain carbon, that is a propyl chloride or propyl bromide. And on nucleophilic substitution reaction, we'll get required product. How we can see in the first with sodium metal, and it's giving sodium propionylate. This on react with the 3-membered alkyl halide, 3-carbon alkyl, propyl 1-bromopropane. If you take 2-bromopropane, we'll get another alkyne, not this alkyne, branched alkyne. What our aim is to prepare 2-hexane. So that's why we are taking normal chain, primary alkyl halide. So on substitution, nuclear reaction, bromine is eliminated as Br minus. This nucleophile replaces bromine by getting our final required product. It is hexane. How hexane? 1, 2, 3. Okay. 2, 3, 4, 5, 6 carbon. Numbering from here. That's why it's a 2 hexane. So in this way, we have prepared propyne 2 hexane. So this way, we can not only propyne 2 hexane or any type of alkyne we can synthesize from this method. So what are doing? We are converting alkynes, especially terminal alkynes, into corresponding carbanions using a metal or any base or Grignard reagent. When it forms its corresponding carbanion, on react with the required alkyl halide, we are getting alkylated alkyne, our required higher homologue of alkyne. In this way, we can synthesize our alkynes. So this is our today's class. What we have discussed in this class, once again, a recap. In the first, we have discussed what is a haloform reaction. Haloform reaction is a reaction in which methyl ketones or potential methyl ketones, when they react with the halogen in presence of excess halogen and well as base, it gives corresponding trihalomethane, which are called haloform, maybe bromoform or maybe iodoform or chloroform. Generally we use iodine, that's why we call as this reaction also iodoform reaction, which is used in organic chemistry or chemical lab to identify methyl ketones to differentiate methyl ketones from other ketones. Okay, it's a we have discussed the mechanism too. In the second, we discussed what are terminal alkynes, what are non-terminal alkynes with examples. Why terminal alkynes show acidic nature we explained because of carbon sp carbon which is having more s character. Due to this s character, these are highly electronegative. That's why the attached hydrogen goes as H plus due to bond polarization towards the carbon. That's why those are acidic nature. They show acidity, weakly acidic nature. So basing on this acidic nature, they forms this corresponding carbanions. These carbanions are used to in different reactions. Like by using these carbanions, we can prepare or we can synthesize required our higher homologue of alkynes. So how to synthesize smaller alkynes to how to convert some smaller alkynes to higher alkynes we have discussed. So with this, I am closing this chapter. Thank you very much.